The liquid-liquid solutions can be ideal solution or non-ideal solutions on the basis of Raoult's law. Okay, just a second. Okay, so ideal solutions will be those ones which follow Raoult's law. Non-ideal, they do not follow Raoult's law. So ideal solutions which obey Raoult's law. And what is about that? That there is no change in enthalpy and there is no change in volume. Means when we mix the two liquids, there is no change in enthalpy. Energy doesn't go out or doesn't get in, and no change in volume of the mixture. These conditions you need to remember. Ideal solutions. And when we talk about ideal solution, the graph of the vapor pressure with respect to mole fraction in the solvent will be straight line as it was. We considered the ideal solutions till now. The liquid-liquid solution we were talking about ideal solution. That's why the graph was a straight line. Okay. P1 was P1 not X1. This was a straight line because we considered ideal solution. If the and in ideal solution, what are the other characteristics? Other characteristics are if the intermolecular attractive forces between AA and BB means we are mixing A and B. Okay. A type of liquid will have A bonds. The molecules will be attached to one another. One molecule of A will have force of attraction with other molecule. In B liquid, one molecule of B will have force of attraction with another molecule of B. When they form the solution, then solution will be formed only if there is force of attraction between A and B, the molecule of liquid A and the molecule of liquid B. In ideal case, these forces of attraction will be equal or nearly equal. So AA and BB are nearly equal to those between AB. Means all three will be nearly equal to each other, force of attraction. And that's why there will be no heat released, no heat absorbed, because the bond enthalpy, the force of attraction is not changing. So it leads to formation of ideal solution. So condition for ideal solution formation, delta H of the mixture 0, delta V of the mixture 0, and the force of attraction between AA, BB, and AB molecules is nearly same. A perfectly ideal solution is rare, but some solutions are nearly ideal in behavior. And the examples are important. These examples are asked. So you need to memorize all the examples. So examples of ideal solution, nearly ideal basically. N-hexane and N-heptane. These both form ideal solution. Bromoethane and chloroethane. Then benzene and toluene. If these are mixed, then these form ideal solution, almost ideal solutions. Yastika, enthalpy will not change because force of attraction is not changing. Understand the difference. Enthalpy will change. Suppose I have A plus B, AB. Okay. Or write it rather in a different way. AA plus BB. And here I have AB and AB, two molecules of AB. Okay. Two attachments. This is the solution because here it is mixed. Now, if you consider energy here and energy of the product, it is same because here energy required to break the association. I'm not calling it bonding, okay, because it is not actually bonding here. Break the association, it may not be bonding, it can be just van der Waals force. But energy required to break the association is X plus X. Here energy required is 2x because it is same, it is written nearly equal. AA, BB, and AB. The intermolecular attractive force is same. So energy required will be same. So in this form 2x, in this form 2x, so there is no change in enthalpy. That's why delta X of the mixture is 0, final minus initial. Is that clear now? This part is important. Examples have been asked quite a few times. N-hexane, N-heptane, bromoethane, chloroethane, benzene, and toluene. These are all examples of ideal solutions. Non-ideal solutions, when a solution does not obey Raoult's law, then it is non-ideal solution. And there are two cases possible we will be talking about. In this case, vapor pressure of such a solution is either higher or lower. So depending on two types of non-ideal solution. If it is higher, the solution is said to be showing positive deviation. If the vapor pressure is lower, we say it shows negative deviation. Why we call it positive and negative, I'll explain through diagram. But first try to remember, if the resultant vapor pressure means the vapor pressure after mixing the liquids, vapor pressure of the mixture is greater than the vapor pressure of individual liquids. Individual liquids A, B, okay. Individual liquids are AA and BB. So vapor pressure will be, some vapor pressure will be here, say P1, P2, and vapor pressure here of the mixture. So if this is higher, this vapor pressure is higher after mixing, then we say it shows positive deviation from Raoult's law. If the vapor pressure of the resultant mixture is lower than the individual components P1 and P2, then we say it is negative deviation from Raoult's law. These are non-ideal solutions. That's why vapor pressure is not same. It is either higher or lower, higher positive deviation, lower negative deviation. Okay. So that's why positive and negative, higher means positive, lower means negative. So if you see the diagram, from diagram it is clear. In first case, the green lines show these green lines. These show the ideal behavior. Okay. So I'm showing this one green line. Okay. This is green line. And this one is green line. Okay. This one is green line. These show ideal behavior. Okay. Ideal behavior. But the blue lines are actually non-ideal behavior. So if the vapor pressure are greater than, vapor pressure are higher than the ideal vapor pressure, In all cases, you see vapor pressures are higher than ideal vapor pressure. So this is considered positive deviation. Positive deviation means it is greater than the expected vapor pressure. But if it is lower, this is lower than the actual one, ideal one. So this one is lower. That's why it is called negative deviation from the ideal behavior. And ideal behavior is shown by Raoult's law. So we say negative deviation from Raoult's law. Positive deviation means the resultant vapor pressure is greater than ideal. Negative deviation is the resultant vapor pressure is less than ideal or less than the individual vapor pressure. Okay. Now, in case of positive deviation from Raoult's law, what will happen? And this is something you need to understand. What I am saying in simple terms, Divya, when we mix two liquids, there will be some vapor pressure of the mixture. If this vapor pressure of the mixture is higher, okay, then the predicted value by Raoult's law. Raoult's law means ideal value. So predicted value by Raoult's law is ideal value. So if it is greater than that, we say it is positive deviation. If the vapor pressure of the resultant mixture after mixing, whatever is the vapor pressure, if it is lower than the predicted by Raoult's law means ideal one, then we say negative deviation. And why it is related to, that's what I am going to explain now. That why it is higher or why it is lower. Okay. To understand why it could be higher or lower, it depends on the force of attraction between the A and B molecules in the resultant mixture is greater than AAAB or it is BB or it is less than AABB. Okay. So you know that you have one liquid, you have another liquid. When these are mixed, you get solution. A and B now have force of attraction. Okay. So this force of attraction can be weaker or stronger than these force of attraction. In ideal case, I told you that all these three will be equal in ideal case. But if these three are not equal, then there are two possibilities. Either the resultant one will have stronger bond or will have weaker bond, if not same. So depending on that, we will have either positive deviation or negative deviation. So for positive deviation, AB interaction means mixture. In the mixture, the AB interactions, remember I am not calling it bond, I am calling it interactions here because this can be van der Waals force. AB interactions are weaker. Now, how come weaker interaction result in positive deviation means greater vapor pressure? Positive deviation means higher vapor pressure. This is something we have talked about in previous slide. Higher vapor pressure of the mixture. That's what we call positive deviation. It will be because if we have the solution when we mix AB, AB, and if these associations, interactions are weaker, it means these two molecules can get separated easily. Because the interaction is weaker. They are not bonded, they are not attracted towards each other with greater force. So less energy will be required to make them apart, A and B. So if we can make them apart, they can get vaporized easily. All three are interrelated. If the forces of attraction are weaker, the A and B molecules can get separated easily with less amount of energy. If they can get separated easily, they can get vaporized easily because they are not attached to one another. They are free. It means if they can vaporize easily, can get vaporized easily, it means they will result in higher vapor pressure. There will be more vapors, higher vapor pressure. That's why positive deviation. So all these are interrelated. Weaker interactions will result in easier separation of A and B molecules, means they can get vaporized easily, higher vapor pressure than predicted by Raoult's law. It means positive deviation. Is that clear? Okay. So these parts are interrelated. You have to remember the questions will be indirectly there. All these are interrelated. These steps are interrelated. Examples: mixture of ethanol and acetone shows positive deviation. All these examples should be on your fingertips. All these examples, whatever we talked about in case of ideal solutions, okay? Or now I am talking about positive deviation, then I will be talking about negative deviation, then I will be talking about azeotropes. Whatever examples are very important. So ethanol and acetone show positive deviation from Raoult's law. Why? Because in pure ethanol, molecules are hydrogen bonded. This is basically the answer of a question. So pay attention here. In pure ethanol, molecules are hydrogen bonded. So if it is ethanol interaction, it is strong due to hydrogen bonding. Okay. On adding acetone, molecules of acetone. So it is written molecules get in between, basically molecules of acetone get in between the host molecule. Host molecule means ethanol. So earlier ethanol, another ethanol, they were hydrogen bonded. Here another one, hydrogen bonded. Here another one, hydrogen bonded. But when acetone is mixed, few acetone molecules come in between. So these acetone molecules break the hydrogen bonding, and they themselves do not have hydrogen bonding between ethanol and acetone. The extent of hydrogen bonding is not good. So they break some of the hydrogen bonds between them. So due to weakening of interactions, the solution shows positive deviation from Raoult law. Now the molecules of acetone and ethanol are not bonded so strongly as ethanol molecules were bonded earlier. Okay. So acetone itself is not does not impact it. Acetone, there was no hydrogen bonding in the solution. Also, there is no hydrogen bonding, but it decreased the force of attraction between acetone and ethanol and ethanol also. So that's why resultant molecules are not so strongly bonded. They can get evaporated easily as compared to the individual liquids. So due to weakening of interactions, the solution shows positive deviation from Raoult's law. Greater vapors will be available, greater vapor pressure, positive deviation. Ethanol and acetone. Example. Now, in a solution formed by carbon disulfide and acetone also, positive deviation. So here acetone is same, reason is different. Okay, I'll explain the reason. Carbon disulfide and acetone show positive deviation here. Okay, ethanol and acetone also show positive deviation. Carbon disulfide and acetone also show positive deviation. Now here the reason is different. The reason is that dipolar interactions between solute solvent molecule are weaker than the respective interactions among the solute solute and solvent solvent molecules. So here we are talking about the dipolar interactions, dipole interactions. Okay? So dipole dipole interactions are weaker in this case. So if you consider CS2 carbon disulfide, okay, so carbon and sulfur basically here it is electronegative, it is electropositive. So if there is another carbon sulfur, I'm just showing CS bond, okay, plus minus, so there is force of attraction between these two molecules. Okay, due to polarity difference. Similarly, there is force of attraction between acetone and acetone also. Okay, so you have CH3COCH3 acetone, okay? And you have another acetone COCH3CH3. So there is force of attraction here because this CO bond is polar. Due to this, there is force of attraction between partial charges, negative and positive partial charges. So in both carbon disulfide and acetone, there are dipole charges, dipole interactions. But when we add these two, the resultant dipole attractions between this molecule, say one molecule of acetone and the other molecule of carbon disulfide, this force of attraction is weaker. So that's why it can get evaporated easily, the molecules, and vapor pressure will be higher, positive deviation from Raoult's law. Example, first one for positive, ethanol and acetone. Second, carbon disulfide and acetone. Both positive deviation from Raoult's law. Reason different. In case of ethanol and acetone, the reason is hydrogen bonding in ethanol before mixing. In case of carbon disulfide and acetone, the reason is weaker dipole interactions after mixing. Dipole interactions were earlier and also after mixing, but weaker. Negative deviation. It will be negative deviation means the force of attraction in the molecules of the mixture will be stronger. Okay. Mixture now will be stronger. It means intermolecular attractive forces between AA and AB will be weaker than the mixture. In mixture, it will be stronger. AA and BB will be weaker than the mixture. It leads to decrease in vapor pressure. Now A and B interactions are very strong, or you can say stronger. A stronger interaction means more energy required. More energy required means not vaporized easily. More energy required to break the association. Not vaporized easily. Not vaporized easily means less vapor pressure, means negative deviation. Yeah. Now this is how it is written in NCERT that intermolecular attractive forces between AA and BB are weaker than those AB. However, it is better to memorize it like that. The resulting interactions are stronger than the interactions before mixing. Yes, Deb, correct. Okay, opposite of positive deviation. So example here, mixture of phenol and aniline. Examples are very important. Mixtures of phenol and aniline. In this case, the intermolecular hydrogen bonding between phenolic proton and lone pair on nitrogen atom of aniline is stronger. So basically, hydrogen bonding, extent of hydrogen bonding is more. Strong hydrogen bonding takes place now. Okay, the hydrogen bonding is now stronger, and the reason is the phenolic proton and the lone pair on the nitrogen, they have very high interaction. How? Understand it. So it is OH, partial negative charge, partial positive charge. And you have another molecule of aniline, NH2. This nitrogen has electrons. So there is hydrogen bonding between hydrogen and nitrogen. Hydrogen bonding is with nitrogen, oxygen, and fluorine only. You know that when hydrogen has interaction with dipole interaction with nitrogen, oxygen, and fluorine. So here with nitrogen, this is stronger. So resultant molecule have stronger interactions due to stronger hydrogen bonding. So difficult to separate, stronger. That's why require more energy to get separated. Means less volatile, means less vapor pressure, means negative deviation. Phenol and aniline. Reasons you must remember. All these are actually very important questions I am talking about at the moment. Next example, chloroform and acetone. Acetone appears in three examples. Both examples of positive deviation and one example of negative deviation. Chloroform and acetone. This is because chloroform molecule is able to form hydrogen bond with acetone molecule. In this case, if you see, both the reasons are similar. In previous case, when I discussed phenol and alanine, mixture had stronger hydrogen bonding. Okay. There I said stronger hydrogen bonding. Remember the difference what I am talking about. Okay. Stronger hydrogen bonding in this case, phenol and aniline. Because some extent of hydrogen bonding is there between nitrogen and hydrogen. Okay. In phenol, we have oxygen and hydrogen. So oxygen of one phenol molecule has hydrogen bonding with hydrogen of other molecules. So hydrogen bonding is still there. In aniline also hydrogen bonding is there. Some hydrogen bonding is there because nitrogen of one and hydrogen of the other one, they have some hydrogen bonding. Okay. But the reason it is not stronger because this hydrogen doesn't have the partial greater partial charge. The hydrogen here is connected to nitrogen. Okay. You know that it will be like this. And here nitrogen of another H2. So this hydrogen doesn't have much positive charge because it is connected to nitrogen here in this case. Okay. And nitrogen, you know, is less electronegative than oxygen. Okay. Oxygen is more electronegative. So if we consider the phenol, then OH, in that case, the oxygen is more electronegative and this hydrogen has partial charge which is greater than what you have in aniline. So that's why when it is closer to nitrogen, the force of attraction is higher, yeah, between lone pair and positive charge. So here I am saying stronger hydrogen bonding takes place. Hydrogen bonding was there, but stronger hydrogen bonding in mixture in case of phenol and aniline. In case of chloroform and acetone, it is again hydrogen bonding, but the slight difference is that here it is extent of hydrogen bonding, means how much hydrogen bonding is taking place instead of the stronger hydrogen bonding or weaker hydrogen bonding. So earlier, there was no hydrogen bonding, but when we mix, then hydrogen of the chloroform and oxygen of the acetone, they start hydrogen bonding. So due to this, they require more energy to get separated. More energy means less volatile. Less volatile means less vapor pressure. Less vapor pressure means negative deviation. So this decreases the escaping tendency of molecules for each component and consequently the vapor pressure decreases, resulting in negative deviation from Raoult's law. Now tell me if anything is not clear. Next, azeotropes. This concept again frequently asked in examinations and also important from competitive examination perspective. First definition. Okay. How we define azeotropes. Some liquids on mixing form azeotropes, which are binary mixtures, means we are talking about two liquids only. Binary mixtures means two liquids having the same composition in liquid and vapor phase. Same composition in liquid as well as vapor phase and boil at constant temperature. These are actually interrelated. If they have same composition in vapor phase and liquid phase, they will boil at the same temperature. Only then it is possible that they will have same composition. What it means, understanding. Suppose we have a mixture of two liquids, L1 and L2, and say L1 is 80% and L2 is 20%. Yeah, this is the mixture. And we start boiling it and we try to get them separated, for example, by distillation. So we start heating this. Now, what we will find in case of azeotrops, that the composition in vapor phase, here we have vapor, composition in vapor phase will be same 80%, 20%. It means we can't separate. Whatever was the composition in liquid form, the same is the composition in vapor form. So distillation won't work. And it will happen when they have same boiling point. Both will get evaporated at the same rate. So same composition. These type of mixtures are known as azeotropes, which have same composition in liquid as well as vapor phase and boil at same temperature. So first understand the definition, then I'll talk about the two different types of azeotropes and why we call them, minimum boiling azeotropes and maximum boiling azeotropes. Composition means percentage. Here, for example, you remember the 11th grade law of constant composition. Okay, that is actually law of constant proportion, means constant percentage. Composition means how much it is, how much it is composed of. Yes, Tika, there are specific examples, that's why. Okay, not all the liquids can form azeotropes. Specific liquids, when mixed, can form azeotropes. Okay. All examples are very important. So till now, I have discussed examples of ideal solutions as per Raoult's law. Then I discussed the examples of for positive deviation from Raoult's law, then for negative deviation from Raoult's law. Now the examples for azeotropes, minimum boiling azeotropes and maximum boiling azeotropes examples are important again. So this is the definition, that if we boil these, the composition which was there in liquid phase, the same will be in vapor phase and they will have same boiling point. So in such cases, it is not possible to separate the components by even fractional distillation. Distillation is something where the difference in boiling point is considerable difference, substantial difference. And fractional distillation is used when the difference in boiling point is around 20, 25 degrees Celsius. Okay. So very, very small difference between the boiling points, then we use fractional distillation. Otherwise, for large difference in boiling points, we can use just distillation. In this case, we can't use even fractional distillation. So this happens because when an azeotrope is boiled, the vapor has the same proportion of constituents as the unboiled mixture. So there is no difference. So there is no benefit of boiling. Now there are two types of azeotropes, minimum boiling azeotropes and maximum boiling azeotropes. It depends on, after mixing, whether their boiling point goes down than the individual components or it goes up than the individual components. Depending on that, the definition. So minimum boiling azeotropes. A minimum boiling azeotrope is a liquid mixture that has lower boiling point than its individual parts. So if I have L1 and L2, boiling point, say here it is 60 degrees Celsius and boiling point here is 70 degrees Celsius. When I mix, the mixture has 50 degrees Celsius. So if after mixing, the boiling point goes down, is lower than the individual parts, then these type of azeotropes will be called minimum boiling azeotrope. Okay. The perfect name could have been lower boiling azeotropes. Okay. Because it is just lower than the individual components, but that is the name given to these type of azeotropes, minimum boiling azeotropes. So here by minimum we mean lower. Resultant mixture has lower boiling point than individual components. So the solutions which show a large positive deviation. So these are interrelated things. So you need to remember from Raoult's law form minimum boiling azeotropes. You know why? Because positive deviation means they can get vaporized easily. They have greater vapor pressure. All these things are interrelated. Positive deviation. Why positive deviation was there? Positive deviation was there because it had higher vapor pressure. That's why we said it has positive deviation. It will have higher vapor pressure if its boiling point is low. Only then at the same temperature, it will have greater vapor pressure, vapors. Boiling point is low of the mixture. It is called minimum. Who has switched on the mic? Deepika, I'm muting you. That's why minimum, and that is the definition, minimum boiling azeotrope. The definition of minimum boiling azeotrope is that the mixture will have lower boiling point than its individual components. So these are interrelated. Positive deviation, minimum boiling azeotropes. And very large positive deviation ones will show the minimum boiling azeotropes. So remember, it is positive deviation. I have explained why. But minimum boiling azeotrope has another condition. The condition is that the composition in liquid phase and vapor phase will be same. It will be possible when it is large positive deviation, not just positive deviation. Large positive deviation only in that case. Shashwat, because solutions need lower energy. Yes, correct. Solutions need lower energy now to get evaporated. So that's why lower boiling point. So minimum boiling azeotropes, large positive deviation. Just remember these relationships. Example of minimum boiling azeotropes. Ethanol water mixture obtained by fermentation of sugar. Fermentation of sugar gives us ethanol water mixture. On fractional distillation gives a solution containing approximately 95% by volume of ethanol. You know fermentation by yeast. This is the process even you are studying from your 7th, 8th grade. Sugar plus water, and this process is known as fermentation. Yeast will give you alcohol in 4 5 hours. This is actually an example of minimum boiling azeotrope. So here also you will get alcohol plus water. Alcohol will be 95%, water will be 5%. This is a mixture and an example of minimum boiling azeotrope. If you want to separate this, you will not be able to separate by fractional distillation because the composition in liquid phase will be 95% 5%. In vapor phase also it will be 95% 5%. So the mixture will have lower boiling point, yeah, by of either of alcohol and water. So this mixture boiling point will be less than of both these boiling points, alcohol and water. That's why large positive deviation. Example you need to memorize. All these examples important. So once this composition known as azeotrope composition has been achieved, the liquid and vapor have the same composition and no further separation occurs. After that, you can't separate by distillation. Maximum boiling azeotropes, opposite of that one. A maximum boiling azeotrope is a liquid mixture, binary liquid mixture that has higher boiling point than its individual parts. If you have L1 and L2, boiling point 50 degrees Celsius and 60 degrees Celsius, the mixture will have higher boiling point than both L1 and L2, 70 degrees Celsius. Say. These type of mixtures will be called maximum boiling azeotropes. So the solutions that show large negative deviation from Raoult's law form maximum boiling azeotropes. Opposite of minimum boiling azeotrope. Large positive deviation, minimum boiling azeotrope. Large negative deviation, maximum boiling azeotrope. Example, nitric acid and water is an example of this class of azeotrope. This azeotrope has the approximate composition of 68% nitric acid and 32% water by mass with a boiling point of 393.5 Kelvin, which is greater than the boiling points of both nitric acid and water. That's why maximum boiling azeotrope, greater boiling point than individual components, maximum boiling azeotrope, large negative deviation. Large negative deviation means lower vapor pressure. Lower vapor pressure means it will require more energy to get vaporized. So higher boiling point. All these interrelations should be clear. No, Shashwat, no. It will be greater than individual components, okay? And that too large difference. Okay? That's why. So nitric acid and water, example of maximum boiling azeotrope. Alcohol and water, 95% alcohol, 5% water, example of minimum boiling azeotrope. Large positive deviation. Maximum boiling azeotrope, nitric acid and water, 68%, 32%. Now the colligative properties and determination of molar mass, the next section. And this is important section basically. Many questions appear from this one. So this is the major part from where questions appear. I'm not saying that this is the only part from questions appear. This is the major part from where questions appear in your examination. Okay. So the vapor pressure of solution decreases when a non-volatile solute is added to a volatile solvent. This is something I talked about in previous class, that if non-volatile solute is added, earlier say there are only water molecules on the surface. And if you add some non-volatile solute, so there will be some molecules here of that solute also, and these will not get vaporized. It means vapor pressure will decrease. Now, not so many molecules will get vaporized as earlier. Okay. So vapor pressure of solution decreases if a non-volatile solute is added to a volatile solvent. There are many properties of solutions which are connected with this decrease of vapor pressure. Okay. Other properties, many properties. First is relative lowering of vapor pressure. This is something we have talked about. Okay. Vapor pressure decreases. But apart from vapor pressure, others, depression in freezing point. So what I am talking about, understand it very clearly. I am talking about if in a volatile solvent, I add non-volatile solute. This is volatile solvent. I am adding non-volatile solute. Then this will happen. All these four will happen. The vapor pressure will get decreased. The freezing point will get decreased. Depression of freezing point means decrease, will decrease. Boiling point will increase. And osmotic pressure will also change. That is something I'll explain. So these all four will have impact of adding non-volatile solute in volatile solvent. Okay. Moreover, before I proceed, now onwards, the convention will be slightly different from what you have studied in 11th. Okay. In 11th, basically, normally we consider solute as first component and this one as second component. Normally, we say that we added W1 grams of solute. Okay, so we consider this one as one, first part. In this chapter, this component solvent is first because solute we add afterwards. This will be always considered as two. So if it is written as W1, W1 will always be of solvent, not of solute. And this is the common mistake students do initially. W2 mass will be of solute. W1, whatever is one, solvent. Whatever is two, that is being added into it after that, two. So these four properties, what I talked about, these depend on the number of solute particles, not the nature. And that is the definition of colligative property. So if you see this term means the properties which depend on number of non-volatile solute particles, not on the nature of particles. Means not on what is its molar mass, okay, what is the structure, rather just the number of solute particles. Those properties are known as colligative properties. So all these properties means relative lowering in vapor pressure, depression of freezing point, elevation of boiling point, and osmotic pressure of the solution. All these depend on how many molecules are added of the solute, irrespective of their nature relative to total number of particles present in the solution. Such properties are called colligative properties. So this is asked as objective question as well, that colligative properties are those ones which, and then you need to select the option which says which depend on the number of particles, not the nature of the particles. So first one, the relative lowering of vapor pressure. The relative lowering of vapor pressure. So lowering in vapor pressure will be whatever is vapor pressure finally and whatever the vapor pressure initially. So relative lowering vapor pressure, if we consider, normally we say, it is final minus initial. That's the convention normally. Okay, final minus initial. But if we are saying it lowering in, then we don't need to put the negative sign. Remember what I am saying. You can understand it from the profit loss concept of mathematics. If I say the formula for percentage profit is the sale price, okay, selling price minus cost price divided by cost price into 100. That's what you do. Or you say profit is simply selling price minus cost price. This is the profit. I'm not talking about, other overheads, etc. in simple terms. But suppose selling price is 120 and cost price was 150, so it comes out to be negative. So I don't say profit is 30 degree, rather I say loss is 30 rupees. Loss is 30 rupees. That's what I say. Okay. So in this case, it is actually loss is initial value minus final value. Initial is cost price, final is selling price, means 150 was cost price, selling price was 120. So here also we will apply the same logic because we are saying it is lowering. So it means initially it was greater and finally it was lower. So lowering in vapor pressure will be initial value minus final value. Okay. So don't get confused that we calculate delta always as final minus initial, but here we are saying initial minus final because we are considering it as lowering. That's why. And this is something you know, P1 is equal to X1, P1 naught. This is Raoult's law. Okay. And initially there was only the pure liquid. So if it was pure solvent initially, nothing else, only solvent, the pressure was P1 not due to this one. There was nothing else. But when we added solute particles into it, its pressure decreased and became P1. So the relationship is P1 equals to X1 P1 naught as per Raoult's law. We know that. And lowering in vapor pressure, I'm not saying relative. I'm just saying lowering here. Lowering in vapor pressure will be whatever it was initially and then whatever it was finally. And this value I'll substitute from here. It will be P1 naught minus P1 naught X1. That is P1 naught 1 minus X1. Okay. And 1 minus X1 I know is X2. X1 plus X2 will be 1. The sum of all mole fractions is 1. So it means delta P1 is equal to X2 P1 naught. Remember, still we have not calculated relative lowering. Now, if we say relative lowering, it means whatever is with respect to initial value. So relative lowering will be delta P1 divided by P1. This is relative lowering. Lowering is just delta P1. Relative lowering means with respect to initial pressure. Initial pressure was P1 naught. Okay. So delta P1, we know it is P1 naught minus P1 divided by P1 naught equals to X2. Why X2? Because this one is X2 P1 naught. So if I write delta P1 divided by P1 naught, delta P1 is X2 P1 naught divided by P1 naught. P1 naught, P1 naught got cancelled. It is equal to X2. So that's why X2. Hence we can say P1 naught minus P1 divided by P1 naught, this value is equal to mole fraction of second component X2. It means N2 divided by N1 plus N2. So tell me now, this is mole fraction of what? This is mole fraction of what? Shivangi correct. Ashi correct. Shashwat correct. Everyone. Arohi yes. Mehak yes. X2 is mole fraction of what? Those who are not responding, I am considering them as wrong answers because it means you don't know. Divya, it is X2. How can it be of component 1, 2, suffix 2? And I told you whatever is 2 is related to, yes, Preeta, correct. Ahan, what is component 2? Varsha, what is component 2? Yes, Varsha, correct. Divya, correct. Okay, now. So component 2 is solute. So it means whenever it is written X2, it is mole fraction of solute. This formula will be used. So write it, memorize it. Derivation has not been asked in 6 7 years as per CBSE guidelines. In chemistry, derivations should not be asked. Application based questions should be asked, or concept based questions should be asked, but not derivation. So memorize the formula. So this is actually relative lowering of vapor pressure. Difference in vapor pressure divided by initial pressure is relative lowering of vapor pressure, and this is mole fraction of solute. Now, mole fraction of solute, if we consider if the amount of solute is very, very small, then here in this case, I can neglect this N2 as compared to N1. N1 is solvent. So solvent is large quantity, but solute dissolved is of very small quantity. So N2 you can't neglect itself. With itself you can't neglect. Okay, but N2 you can neglect as compared to N1 component. So the number of moles of solute can be neglected as compared to number of moles of solvent. So if it is the case, it will be reduced to N2 divided by N1. It was N1 plus N2. This is neglected. And you know the number of moles is given mass upon molar mass. So N2 W2 upon M2, W2 upon M2 given mass upon molar mass, N1 given mass upon molar mass. When you simplify this one, you will get this. Will be equal to W2 upon M2 into M1 by W. W reciprocal of this one if you multiply this. This is again very important, and this is the one formula which will be used most frequently in this part. Okay, in this part of the chapter. You will be using both formula. This one, if you are calculating in terms of number of moles, okay, or this one, if we are talking about in terms of mass and molar mass. Both are same formulas basically. Here, number of moles have been written as given mass divided by molar mass, nothing else. N2 is solute, not solvent. This is I tell again and again because students still make mistakes despite telling them so many times. Now there's a question. The vapor pressure of pure benzene at certain temperature is 0.850 bar. A non-volatile, non-electrolytic solution weighing zero point 0.5 gram when added to 39 grams of benzene, molar mass 78 grams per mole. Vapor pressure of the solution then is 0.845 bar. What is the molar mass of the solid substance? Everything is given related to formula, you know, you can tell me the answer. I'm giving you a few hints. Okay. Vapor pressure of pure benzene at, so P1 naught is given 0.850. Benzene here is solute. Okay. A non-volatile and solvent, sorry. Benzene is solvent and that's why 1. Non-volatile, non-electrolytic solid weighing. Now solid means it is solute, W2, 0.5 gram. Added to 39 gram of benzene. Benzene is solvent, that is 1, 39 grams. Molar mass of benzene M1, 78 grams per mole. Vapor pressure of the solution then is, means P1 is 0.845 bar. Final. Okay? It decreases from 0.850 to 0.845. You need to calculate M2, molar mass of the solid substance. Solid. Apply the formula. P1 naught minus P1 divided by P1 naught equals to W2 into M1 by M1 into W, M2 into W1. You have to calculate this part. So first write it in this term or just substitute the values and you can get the answer. The important part initially is to focus on which one is solvent, which one is solute, which one is 1, which one is 2.